In today's lecture, we will explore the world of support vector machines, a powerful tool in machine learning. SVMs are known for their ability to make precise classifications, making them essential in various applications. Let's start with our first block of code. This function is designed to plot the decision boundaries and support vectors for a support vector machine classifier. It takes the trained SVM classifier SVC and input data x and y and some optional parameters for plotting as arguments. As we can see, this line of code takes four parameters. In this line of code, it calculates the minimum and maximum values for first feature column 0 in the input data x and adds and subtracts padding, which is pad value to create the plot's x-axis boundaries. Similarly, over here, the minimum and maximum values of second feature is calculated in the input data x and adds subtracts pad values as well to create the plot y-axis boundaries. Later on, here a mesh grid function is used. It is used to generate grid points for plotting. NP arrange over here is a function in NumPy which is used to create arrays of x and y values within the specified xmin, xmax, ymin, ymax boundaries with the step size of h. In the next line, this line predicts the class labels for each point on the grid by flattening the xx and yy grids using Ravel function and then using the SVM's classifier predict method to make predictions for these flattened points. After this, reshape function is used for reshaping of Z so that we will have same shape as XX grid. This ensures that Z can be used for contour plotting. Over here, contour F method is used. This line creates a field contour plot using the XX, YY, and Z values. It uses color map CMap paired and sets the transparency alpha to 0.2. After this, we will see how scatter plot works. So here scatter function is used. This line creates a scatter plot of the input data points. As you can see over here, these are input data points where the color of each point is determined by a corresponding label y, and S over here is the parameter that controls size of the points. This line over here sets x-axis limits of the plot based on the calculated xmin and xmax values, and same for the y limit values. This scatter method over here works same as scatter method over here. Later on, x label and y label is used to set the labels of the x and y axis of the plot. And this dot show function displays the plot on the screen. Over here, there is a print statement which prints the number of support vectors. Let's move on to our next line of code. In this line of code, over here, we will see how random data is generated for classification. This line of code over here sets the random seed for the NumPy random number generator to 10. Setting a seed ensures that you get the same random numbers every time you run the code, which is useful for reproducibility. Later on in this line of code, we are generating random data in the form of 2D NumPy array X. The npy.random.randn, this function generates random numbers from a standard normal distribution, mean 0 and standard deviation 1. It creates an array with 30 rows, as you can see over here, 30, and 2 columns, effectively generating 30 data points with 2 features each. In our next line of code, this line generates target labels y for the data points. It uses np.repeat method to create an array by repeating the values, example 1 comma 0, 15 times each. As a result, y contains 30 elements, with the first 15 elements being 1 and next 15 elements being 0. This is a binary classification problem where the goal might be to classify data points into two classes labeled as 1 and 0. We will display our first 3 rows and columns now in this line of code using NumPy array slicing. As you can see over here, our start and end is 3. So it'll start from 0 and end till 3. So that's how it will print the array numbers. So over here, we have just printed our first 3 rows of the X array and first 3 elements of Y array. So our slicing works from 0 till 1 element before the end. So that's why 0, 1, and 2 has been printed over here. In our next lines of code, we have already seen scatter function. So what it's doing is it's plotting the data points from X array on a 2D plane where this both values represents first feature and second feature for all data points. This argument over here specifies the colors of the points based on the values in the Y array. And again, these 2 lines of code sets labels for x-axis and y-axis of the plot respectively. In this case, x1 and x2 are used as labels to indicate which features are being plotted on each axis. This is how we have got a scatter plot where data points are displayed in different colors based on their corresponding labels, and axes are labeled as x1 and x2. This can help us visualize the distribution of our data and see if there is any separation between two classes based on features x1 and x2. Moving on to our next lines of code. Here we are going to train a support vector machine classifier. Let's see how we will do it. In this line of code, we are creating an instance of support vector machine classifier using SVC class, as we can see over here, from scikit-learn library. C is equal to 3. This parameter controls the trade-off between maximizing the margin, large C, and minimizing the classification error, small c, in the SVM. A larger C allows for a smaller margin but fewer misclassified points. And in our second argument, the kernel is equal to linear. This parameter specifies that we are using a linear kernel, which means the decision boundary will be a straight line in the feature space. The next line of code, this line uses a fit function which fits which is trains the SVM classifier M on the input data X X and corresponding labels Y. The SVM will learn to find the optimal decision boundary that separates two classes 1 and 0 based on the features in X. And later on, plot underscore SVC. This function calls the plot SVC function that we have defined earlier to visualize the decision boundaries and support vectors of trained SVM classifier. So in this output, we can see that plot SVC function have plotted the decision boundaries, support vectors, and data points on 2D plane, allowing us to visualize how well the SVM has learned to separate two classes. As you can see here, the separation line. So this is how we are seeing SVM's decision boundaries and support vectors in the resulting plot. Uh, and this is helping us to assess performance of the classifier on our data. Let's move on to our next line of code. Over here, m dot coefficient, this attribute of scikit-learn SVM classifier returns the coefficients of the linear decision boundary. However, it's important to note that this attribute is only available when you use a linear kernel, because linear SVMs create linear decision boundaries. And as we can see, we have chosen a linear kernel over here. That is why we are able to use this argument. In the output, we can see that this line of code returns array of shape, where each row of array corresponds to a class and each column corresponds to a feature. The values in this array represents the coefficients of the linear equation defining the decision boundary. In this line of code, we are trying to find the indices of the support vector. So m dot support attribute of the scikit-learn returns an array that contains the indices of support vectors. Support vectors are the data points from the training set that lie closest to the decision boundary and play a crucial role in defining the decision boundary of the SVM. Let's have a look at our next code snippet. These lines of code we have seen earlier as well. So this line over here is just another SVM classifier with a linear kernel, but sets a smaller regularization parameter C to 0.3. As in our earlier example, we have seen C equals to 3, which was a narrower margin and fewer support vectors. Like it showed us narrower margin and fewer support vectors, while the second SVM right over here, this is using C equals to 0.3, and this may have a wider margin and potentially more support vectors. This line over here again trains the second SVM on the same input data X and Y, and again over here this function is used to visualize the decision boundaries and support vectors of the second trained SVM classifier. Thus, by visualizing these SVMs, we can absorb and observe how changing the regularization parameter affects the model's behavior in terms of decision boundaries and support vector placement. This can provide insights into trade-offs between model complexity and generalization in SVM. Let's have a look at our next lines of code. Over here, we will try to select the optimal C parameter by cross-validation. So in this code, we are performing hyperparameter tuning for an SVM classifier with a linear kernel using scikit-learn's grid search CV function for cross-validation. This allows us to find the best value of the regularization parameter C among the range of options. As we can see over here, these are the range of our options. So let's understand step by step how this works. Over here we are defining a list param. This contains a dictionary specifying the hyperparameter grid to search over. In this case, we are tuning the C parameter and we are providing a list of potential values to test. In our next line of code, we are trying to create an instance of grid search CV. This specifies SVC. This specify the kernel equals linear. This specifies that we want to use an SVM classifier with a linear kernel as the base estimator for the grid search. Param over here specifies five-fold cross-validation, which means the data will be split into five subsets and the model will be trained and evaluated five times using a different subset as the validation set each time. Scoring equals accuracy. This we are specifying that we want to use accuracy as the scoring metric to evaluate the performance of different hyperparameter settings. Later on over here, we are training the grid search CV object M on our input data X and labels Y. The grid search will evaluate SVM classifier with different values of C using cross validation and select the best C value based on our accuracy. After we run this code, we get access to the best hyperparameter values and best estimator using the following attributes of grid search CV object M. So we will see in our later code that we are using m dot best params. This will give us the best hyperparameter values found during the grid search, which includes the best C value, and we will see m dot best estimator. This will gives us best SVM classifier with the selected hyperparameter. Let's see what happens in our next line of code. This m.cv underscore results, this attribute of scikit-learn grid search CV object provides detailed information about the cross-validation results for each combination of hyperparameters that were tested during grid search. This information can be useful for analyzing the performance of different hyperparameter setting. So we can find information such as mean fit time, params, standard fit time, mean score time, standard test score, rank test score, information like this. So this mean fit time, what this means is it's an array containing the mean time in seconds taken to fit the estimator on the training data for each parameter setting. Just like that, standard fit time over here is an array containing the standard deviation of the time taken to fit the estimator on the training data. Mean score time over here contains mean time taken to score the estimator. And just like that, standard score time over here is giving us the standard deviation of the time taken to score the estimator on the validation data. Params over here is an array of dictionaries containing the hyperparameter setting for each combination. Param underscore C over here contains an array containing um, values of C parameter that were tested. Just like this, we have more couple of values. Split to test score. This arrays contains the test scores for each fold of the cross validation. And lastly, standard test score gives us array containing the standard deviation of the test scores across all cross validation folds, and rank test score over here gives us array of ranks, the parameter settings based on their mean test scores, with one being the best performing setting. In the next line of code over here, we are trying to access mean test scores from the m.cv underscore results dictionary. This code extracts the array of mean test scores for each combination of hyperparameters that were tested during the grid search. As we have seen before, the best params attribute of a scikit-learn grid search CV provides the hyperparameter values that resulted in the best performance during the grid search. In our case, we have performed a grid search to tune the C parameter for an SVM classifier with a linear kernel. Thus, we can use this best hyperparameter value to configure our SVM classifier with an optimal settings for our specific machine learning problem. In our next line of code, we have seen this code earlier. So after running this code, we will have a test dataset X test with 30 data points having each having two features and corresponding labels. Y test representing two classes 1 and 0. The test dataset can be used to evaluate the performance of machine learning models such as the SVM classifier we have trained earlier or new unseen data. Random.choice method over here. This generates random labels for the test dataset. Uh, it uses this method to randomly select values from the provided array 1, 0. The size of the array is 30, which means we will get 30 random selections of either 1 or 0. Let's work on our next snippet of code. Over here, we are trying to predict y of the test data using best model. So we are using trained support vector machine classifier with a linear kernel and regularization parameter C, which is set to 10 to make predictions on test dataset. And later on, we are trying to compute a confusion matrix to to evaluate the classifier's performance. So we'll check it line by line what's happening over here. Right over here, we are using dot predict function to make predictions on test data X test. The predictions, the predicted tables are stored in the ypred variable. This line of code, what we are trying to do is we are trying to calculate a confusion matrix to evaluate the performance of the classifier on the test data. The confusion matrix function from scikit-learn computes the confusion matrix and we wrap it in a pandas data frame for a better visualization. Y-test over here contains the true labels for the test data. Ypred over here contains predicted labels generated by SVM classifier. M.classes is used to specify class labels for the rows and columns of the confusion matrix. Thus, this resulting data frame will display the confusion matrix, which provides information about the number of true positives, like here true positive, true negative, false positives, false negatives, allowing us to access the classifier's performance on test data. Moving on to our next line of code, we are trying to create linearly separable data over here. Over here, we are trying to modify the x1 array which is equivalent to x test based on the condition where y1 is equivalent to y test is equal to 1. Specifically, we are subtracting 3 from the elements of x1 that correspond to instances where y1 is equal to 1. This appears to be a data transformation where we are modifying the features of a subset of the test data. Let's dive deeper into this line of code. Over here, this line of code is modifying the elements of the x1 array based on a condition. Specifically, it subtracts three elements from the elements of x1 where corresponding values in y1 are equal to 1. The condition y1 equals to 1 creates a Boolean mask that selects the elements in x1 where y1 is equal to 1. And over here, this line of code subtracts 3 from those selected elements in x1. Thus, this code effectively transforms the feature of a subset of a test data x1 where the corresponding labels are equal to 1, which is y1. In our next line of code, we will try to create a scatter plot to visualize test data x test with labels y test. Uh, let's see how this will work. So as we have seen this function before, this line of code is using scatter function from matplotlib, and it's taking xtest as a parameter, which specifies the x and y coordinates for each data point in the test dataset. Later on, c equals to ytest determines the colors of the points based on the values in the ytest array. This x label and y label gives us the names of x-axis and y-axis. So over here we have a scatter plot where data points are displayed in different colors, yellow and blue, based on their corresponding labels, and the axes are labeled as x1 and x2. This is allowing us to visually inspect the distribution of our test data and see how well it aligns with the original data or any transformation we have applied. Now, in these lines of code, we will try to train an SVM classifier on our modified test data x1 and corresponding labels y1. After training the model, we will use plot underscore svc function to visualize the decision boundaries and support vectors for our modified test data set. So this code will help us to access how the model performs on the modified data and whether the feature transformation had any impact on its performance. We are using larger C value in this code, and that's why we are having smaller margin over here. In our next line of code, we are using smaller C value, and thus we will have larger margin in our output. So in this updated code, we are training the same SVM classifier on the modified test data with smaller C value. Thus, when we compare this output with our previous one, we will have larger margin in our smaller C value and smaller margin in our larger C value. This is how this code snippets we have worked on today demonstrate various aspects of using support vector machines for classification, including handling linearly inseparable data, tuning hyperparameters, and evaluating model performance.